My name is Chiranjib Bhattacharyya. I work in the Department of Computer Science and Automation, Indian Institute of Science. So, I am interested in broad area of machine learning, and today I am going to discuss a very interesting algorithm called the EM algorithm. So, EM algorithm is one of the, if you can say, the workhorse of unsupervised machine learning. Some of you know machine learning has broadly two parts, supervised and unsupervised. And under unsupervised machine learning, one of the interesting or one of the major tasks is to learn about latent variable models. And EM algorithm is the workhorse for learning such models. And today we are going to walk you through these EM algorithm procedure, and we will show you how we can use it to learn at least one latent variable model. So, with this, let's first quickly touch upon latent variable models. As we said that in supervised machine learning, often the task is that you need to learn a function from a data which is often labeled. Let us say the data is represented by vectors x and the label is y. You want to learn a function such that f(x) is equal to y. Right? In unsupervised learning, often these y's are not given. You are often given these data vectors, and you are often asked to build models on that. So, such models are often predicated on the fact that maybe there are some hidden variables which I am unable to observe, and then the idea is, so can I then learn a suitable shall we say a probability distribution on this joint latent and the observed variables. So, this being the philosophical pitch, people often define latent variable models as probabilistic models which describes the relationship between manifest variables and a set of unobserved variables referred to as latent variables. So, hopefully we will try to give you more concrete mathematical examples as we go along. For now, these problems or these models encompass a large variety of models, including factor models, something like PCA, probably principal component analysis, which many of you know is an example of a latent variable model. But the most famous one is probably the mixture models, where often you are given a mixture distribution, but that can also be written as a sort of a latent variable model, where there is a latent variable which indicates which component of the mixture is being used to generate a particular distribution. So, most sophisticated models such as hidden Markov models is another example of a latent variable model. So, idea behind hidden Markov models is that it is trying to model a temporal a sequence of temporal data, and where the temporal data is evolving over time over on a set of hidden variables which obey a sort of a Markov chain dynamics. Inferring all such models often is a difficult task, and here is where EM algorithm comes out handy. So, the objective behind this talk is to walk you through the steps of EM algorithm. Now, to do that, let us introduce some notations. So, here on we will call the manifest variables or the observed random variables as x, and then the latent variables we will call them z. Right. Obviously, as we alluded to, we would like to model the distribution between them, and so there will be two distributions here. One is the joint distribution, which we will call as distribution of z and x, parameterized by the model parameters theta, and often we would also like to understand the posterior distribution, that is given in data x with parameters theta, what is the distribution of z. Now, on to this notation, let us now delve into latent variable models. So, the way we go about understanding latent variable models is we first write down a generative model of the data, that is how the manifest variables are generated from such latent variable models. So, as of now, this notation would indicate that x is distributed as, or x is coming from a model which assigns a probability according to the model parameters theta, right. So, with this, as I said, we are interested in the so called latent variable models. So, generally the latent variables can take two types of values, either they are discrete or they are continuous. For the discrete case, we can mixture distribution as one example, hidden Markov models is another example. For principal component analysis, again we have one can write the same latent variable model, but over a continuous valued latent variable, and hence we use the term integration. So far in this discussion we will confine ourselves to discrete valued latent variables, which would involve summation here. So with this, so let us look at the procedure or the framework for learning such models. So often the situation is this: I am given a data set D, which you can think about as IID draws. IID stands for identical and independently distributed data coming from a particular model. Then the idea is to compute the model parameters. Here I have indicated this theta. So the way we go about doing it is we will invoke the famous maximum likelihood framework, where we want to maximize the likelihood as a function of theta given the data set. So where the likelihood is the summation of the individual likelihoods assigned to particular data points, the n data points, right. So this is the famous log likelihood formula here. Now the challenge here is, because this likelihoods is not directly given but needs to be computed by a step called, which we call as marginalization. That is, we need to integrate out or add or remove the sum over all the values pertaining to the latent variable. So this marginalization step is often introduces computational challenges. So the idea is EM algorithm helps us sidestep this problem. So the EM algorithm, at least the form which probably was first appeared in a seminal paper in 1970s when Baum and Welch were trying to understand hidden Markov models. There is a very nice survey paper by Rabiner where he discusses the Baum-Welch algorithm, and there you can see how the EM algorithm, how you can read a very readable introduction to how EM algorithm was invented by them. However, the EM algorithm which we know is mainly due to Dempster et al. This came out in 1977. So we will present the version due to Dempster et al. In this discussion. So essentially EM algorithm stands for two words: expectation maximization. So it just consists of two steps, the expectation step and the maximization step. The expectation step is given by computing a function q of theta parameterized at theta 0. By this what I mean is, this is like an iterative step. Suppose you have an estimate of the model parameters, and let us call the estimate theta 0. Now the objective is, can I find a new theta which may be better in some sense, a better estimate of theta 0. Alright. So we will hopefully we will make this clear what I mean by better in the coming slides. So for now q theta parameter at theta 0 is given like this. So this is the expectation over zi given expectation of so log of p zi comma xi equal to xi, that is the posterior. So it is the joint log of the joint probability of zi and xi given the data point at small xi with parameters theta. Note that the posterior is computed at theta 0, right. So zi is unknown, so we average over this zi. So over the m step, and so once you computed q theta given theta 0, then theta nu is obtained by maximizing this function q as a function of theta. Now often what happens is that, so you once you do that from theta 0, you can find a new theta, that is theta nu, and then you again theta nu again you repeat this step, hopefully get a better estimate and so on. So often the hope is that, or at least in many cases we will see that this maximization step can be easily computed. So, with this, so in the next few slides we will trying to explain, we will establish two things. We will try to establish what do I mean by getting a better estimate, and we will try to give an example where this is done very easily and where maximum likelihood framework would not have been directly solvable. So, to build this intuition, we will need some background. So, one of the interesting mathematical tools we will use is known as Kullback-Leibler divergence. So, divergence, so it is a measure of a distance, so between two distributions. So, here we will confine ourselves to discrete random variables. So, hence we will take P and Q be two PMFs, and delta D would stand for a probability simplex. A probability simplex is nothing but a d-dimensional vector whose all entries are greater than 0 and the entries sum to 1, right. So, we will call boldface U as belonging to delta D if the entries of U obeys this relationship. Now, let boldface P and boldface Q be two entries in this simplex. So, obviously these are valid PMFs. Now, Kullback-Leibler divergence we will denote it by KL in honor of them. Q comma P is something like Qi log Qi by Pi, sum from I equal 1 through D. Now, it is a very interesting exercise, maybe you can take this as a homework, you can try to do that. You can see KL of Q comma P is always greater than or equal to 0, and it is 0 if and only if P equal to Q. Now, these properties are also obeyed by distances. However, you note that if you switch the roles of P and Q, you will see that you will get different values. However, they will be still greater than 0, right. So, that is why Kullback-Leibler divergence is not called a distance function, but a distance like function, and is often called divergence. So, anyway, so this is so what we will need for this rest of the talk is the property that KL of two PMFs is always greater than or equal to 0, and they are 0 if and only if P equal to Q. So, armed with this Kullback-Leibler divergence, so what we will do is to in our quest for establishing the principles, or let us say the principles behind examining EM algorithm, we will try to derive on inequality. So, now let us assume I have a model M. So, model M lays down the joint probability distribution. So, let us say it is given by the law as given here, that P of x and z is equal to I, etc. This is the model M, let us say. So, often a specific form would be given by the form of the probability, that is in the form of the joint probability, right. Suppose given this likelihood function P of x given theta. Now, we will try to establish the following: for any Q in the probability simplex delta K, right, where K is the number of hidden states the discrete random variable takes, we would like to show that the log likelihood, that is log of Px by theta, is equal to KL of Q comma P plus an entropy term H of Q plus the expected term over log P of x comma z. Now, indicated z is red is because this is to indicate that this expectation is over z, where x is fixed here, right. So, now we will try to establish this relationship. Okay, so this is the definition here, as we said, E of Q is again Qi log P of x z equal to I and theta, and entropy is this. So, fine, we will have to establish this relationship 1, right. So, let us do this now. So, recall, so let us look at KL Q comma P. The KL Q comma P, as definition given few slides back, it can be written as something like Qi log Qi minus logarithm of P, the posterior distribution of z given x, right. This is the KL of Q comma P. Now, as you know, this quantity is greater than 0, right, that is where we will use it later, but for now let us try to open up this expression in terms of the model, right. Now, you see this conditional can be written equivalently as the joint probability of z equal to I and x, and you will divided by log of P of x given theta, and then when you rearrange terms you get an expression like this, where you get a log of Px given theta minus the joint log of joint probability. right, and all of them weighted by the weights Qi. It is now very clear that the entropy function is a negative of this Qi log Qi, so minus h of q. And again, if you look at this minus term, right. So, here we have the expectation over q over z, that is this given by this over this distribution q, right. And then we have this other expression, the sigma I equal 1 through k Qi log p x given theta. Now, you see this log p of x given theta does not depend on Qi, right, it is obvious. So, obviously this we can write it like this, and now since Qi lies in a probability simplex, this value is simply 1. So, this goes away and that gives me this. So, you see this is nothing but the equation 1 which you wrote down, which was our aim, which you wrote down in the previous slide. Yeah, this is nothing but equation 1 then, right. So, we have established equation 1 now. Now, using this we want to build an inequality which we will use later, right. So, now this is the inequality which I was alluding to. So, inequality is of the following form, right. For any theta hat, right, which describes the model, we can lower bound the log likelihood for any arbitrary theta. So, that is log of px given theta is lower bounded by a function L which depends on x and theta, but parameterized at theta hat. So, you see this is a very interesting relationship. It establishes a relationship between theta hat and arbitrary theta, right. So, what is the form of L? The form of L looks like it is that expectation over again z, but over a distribution given by p tilde, where p tilde depends on the posterior distribution of z given x and theta hat. And this inequality can be tight if theta hat is equal to theta, alright. So, this is the inequality we wanted to show. Now, let us see if you can show that. So, the idea is very simple. If we just plug this p hat in the q in the previous equation 1, and noting that the KL, the q comma p is always greater than equal to 0, the inequality follows. It is a straightforward algebra from there. Now, the equality follows by noting that the KL of q comma p is equal to 0 if and only if q equal to p. And now, if you set q equal to p, so whenever p tilde equals to p, our equality would, so basically theta and theta hat agrees, you get p equal to p hat, etc., and then that is where it is, right. So, now using this we will further show a new inequality which is a lower bound of the likelihood. So, now see the log likelihood of the entire data, that is which we showed initially when we wrote down the likelihood function, log likelihood function. So, log likelihood function is lower bounded by the q function which we use to define the EM algorithm, plus another function f of theta 0, right. So, remember theta 0 is the current estimate of the model parameters, right. Q theta given theta 0 was defined in the EM step, right, and L was defined as the log likelihood. Now, let us try to establish that. As we know from definition, the log likelihood is the logarithm of the likelihoods of the observed data points. Now, the inequality which we are denoting is with script I tells us that this is lower bounded by L of that function, right. Now, the L of that function is, if we just write the definition, is given by this expectation over p tilde p of xj equal to xj zj given theta plus the entropy function. And the interesting point is pj hat depends on theta hat, right. Now, if you plug instead of theta hat, now you plug theta 0, you see this term is nothing but our famous q function, and so this entropy term is again a function of theta 0, and that is what we are calling it as the f of theta 0. So, this is the sum of entropy over all the individual examples, right. So, now there is one more interesting fact, right. So, you also noted that the inequality is tight when theta equal to theta tilde in the previous example, right. Now, theta tilde is theta 0, and as a consequence of that we can also see this following relationship now. that the log likelihood of theta 0 given data is equal to q theta 0 at theta 0 plus f of theta 0, right. This is due to the relationship which we had. Now let us so now let us look at the EM algorithm again. Let us recall the EM algorithm. EM algorithm was said this. Now, so we will try to prove that the log likelihood of the new estimate of the model parameters theta nu is larger than the log likelihood of the old estimate theta naught, right. Now, let us try to do the proof. The proof is now plugging in the pieces which we have learned in a few slides before. So, you see the log likelihood of theta nu is strictly greater or less or greater than equal to q theta nu given theta 0 plus f theta 0, right. Now, this immediately implies that the log likelihood at theta nu is greater than q theta theta naught, where theta can be any theta. Why so? Because please recall the theta nu is obtained by maximizing over all thetas, right. Since we are here at this point, we can as well replace theta, since it is for all theta, you can replace theta by theta naught, right. So, then we have managed to prove that the log likelihood of theta nu given given a data set is lower bounded by q at theta naught, parameters at theta naught plus f theta naught. Now, please recall in the previous slide we also showed that that this expression, right, q theta naught plus f theta naught is nothing but L theta naught. So, obviously this establishes then that the likelihood keeps on increasing, right. In that sense, EM algorithm iteratively helps improve the likelihood. In a sense, this is what the EM algorithm does then, right. What it tries to do is it tries to compute a sequence of model parameters theta t, and each step the likelihood tends to be larger. Now, one can show in very general conditions that this converges to a local minimum, all right. So, this is in nutshell what EM algorithm does. So, just to show you the benefits of EM algorithm, so let us try and apply it to a latent variable model. In this case, we will try to apply it to mixture of multivariate Gaussians, and we will call that as a model M. So, you see this is a very important model used in many places. So, what you are given is a mixture distribution. A mixture distribution is given by mixture weights. In this case, it is alpha I, and suppose there are k mixtures. Now, let us assume each of this mixture distribution have a model parameter is parameterized by a multivariate Gaussian with the suitable mu i's and sigma i's. So, our model parameters are that way alpha I, mu I and sigma I equal 1 through k. This is what we have to estimate. Now, one can as well try and fit a log likelihood model, but you will see the equations would get very difficult and messy. On the other hand, EM algorithm gives me very simple updates. So, what we can do is we can, so let us first write the mixture distribution as a latent variable model, where the latent variable can take k values. We denote the weight or the probability that z takes any of the I values as alpha I, and then the conditional distribution that the observed variable has a density given by a Gaussian where z is equal to I is parameterized by mu I sigma I. So, under this model let us apply EM algorithm updates we know. So, what we will do is I will not write down the details, but I will write the final formulas. So, on the jth example, right, we can compute the posterior distribution. This is the thing what I said, z given x at theta 0. Please recall that theta 0 here is alpha 0, mu I 0 and sigma 0, right. So, often these pi tilde j's are often called responsibilities. Now, this is essentially nothing but PMFs. So, if you sum this over for a fixed j, you will get you will get a value 1. EM algorithm step, please recall that we need to compute the probability that z is equal to I given x. So, here assume you take the jth example. So, we define pi tilde p tilde I j, right, where I is the value of the hidden variable and j is the jth data point is given by this. These are often called responsibilities. Now, if you for a fixed j, if you sum over i's, this should sum to 1. This defines a PMF, right. Now, the update equation, this is the maximization step. Once you define this, you can define a suitable Q function, and the maximization step is very simple. It is saying something like alpha I, the new estimate, is something like Ni by n, where Ni is nothing but sum over all j's p tilde ij, right. And the new estimates of mean mu I is basically the responsibilities that each of the jth example is assigned to the ith Gaussian, and similarly for sigma I nu. So, you see this gives you a very simple, easy to use update, right. And so, this is one of the beauties of EM algorithm, though it might look very difficult or contrived, but it is very simple, easy to use updates, and that is why it still is one of the important toolkits in modern day unsupervised machine learning. So, in this talk I tried to walk you through the steps of EM algorithm and to illustrate its benefits by showing how it can be applied to mixture distributions. So, EM algorithm remains one of the tools for learning latent variable models. In today's research often focuses on the problems where the number of hidden states k is quite large. In such cases, either you have to resort to what is known as variational methods or Gibbs sampling, and the idea is that EM still would remain the broader outer algorithm, but inside the E steps and the M steps can be approximated by some of these things, and their interplay is often still an area of study. So, you will find this interplay in many situations, topic models, graphical models, or and many such other examples. So, I would like to conclude by saying that though it was invented something like 30 years ago, but it still remains one of the algorithm in machine learning. So, thank you for listening. I would encourage you to work out the steps which I did not do in this presentation. I hope this would be of some use of people who want to fit latent variable models and in machine learning and interested in machine learning in particular. Thank you for listening.